Please start.
Thank you for introduction. A surface link is a cross-oriented surface F, smoothly embedded in S4. An S2 link, if F consists of two spheres, and a surface node, if F is connected. A surface link F is trivial if F is the boundary of disjoint handle bodies smoothly embedded in R4, and ribbon if F is obtained from trivial S2 large O by surgery, excuse me, along an embedded one-handle system. The pair OH is a ribbon system of the ribbon surface link F. A coded sphere system is a pair O alpha in R4 obtained from OH by replacing replacing H with a core arc system alpha of H. Sorry. H. A coded loop system is a pair O alpha in R3 by replacing O with an equatorial loop system or small o called a best loop system in R3 and by taking alpha in R3 called a code system. The following lemma was found a long time ago. Every ribbon surface link F up to equivalences is uniquely constructed from a coded loop system O alpha in R3. A coded loop diagram in R2 of a coded loop system in R3 is useful for understanding the placement of a ribbon surface link. These pictures are coded sphere system and coded loop diagram. There are three kinds of moves on a coded loop diagram. M0 is the ride master moves as turbulent spatial graphs. M1 is a fusion fission move on best loops along a chord. M2 is a chord moves like these pictures. The following identification theorem is a fast theorem. Every ribbon surface link F in R4 up to equivalences is identified with the chord graph. That is a coded loop diagram modulo the moves M0, M1, M2, where O is considered as the boundary of a disjoint disk system with orientation counterclockwise in R2. So just this right picture, okay, it's a best loop. It's just counterclockwise has just counterclockwise orientation. A virtual graph is an oriented virtual graph diagram with equivalence relation generated by the virtual graph rightmost moves, where the virtual arc is regarded as a virtual notoid. The virtual graph rightmost moves consist of graph rightmost moves, virtual rightmost moves, and optional virtual rightmost moves. These pictures, okay, but the following observation is obtained. A virtual graph inducing a virtual notoid is transformed into a chord graph so that the virtual graph rightmost moves are transformed into combinations of the moves M0, M1, M2, and the virtual group is sent to the fundamental group of the surface link. Okay, how to transform from a virtual graph into a code graph is like these transformation in this picture, these pictures. Next, 200 on surface link F in R4 is a 200 D cross I on F embedded in R4. So that the intersection of D cross I and F is the attaching annulus boundary D cross I. Here I denote a closed interval containing zero with D cross zero, the core disk D of the 200 D cross I. O200 pair on a surface link F is a pair D cross I, D dash cross I of 200 D cross I, D dash cross I on F. So that the intersection of D cross I and D dash cross I is the intersection of the attaching annulus, which is a square. It's a called the plumbing square. So this picture illustrates that thing. For an O200 pair, D cross I, D dash cross I on a surface F, let F D cross I and F D dash cross I be the surface links obtained from F by the surgeries along D cross I and D dash cross I respectively. Let F D cross I, D dash cross I is the union of delta and FC delta, where delta is a plumbing disk. It's just a D cross boundary I. Union, the union of D cross boundary I and Q plumbing, no, Q is a square, okay? And D dash cross boundary I, okay? And FC delta is a complement of the attaching annuli, boundary D cross I and boundary D dash cross I in F. Then there are identifications. There is F D cross I, D dash cross I is equal to F D cross I is equal to F D dash cross I. Okay, by equivalences on three cell moves on the interior of the disk, plumbing disk delta. The following O2 pair uniqueness theorem is obtained. And this is very basic to our argument. For any O200 pairs, D cross I, D dash cross I, and E dash cross I, E cross I, and E dash cross I on a surface link F with the intersection part, intersection annuli coincided. Then there is an equivalence F from F to itself, keeping FC delta fixed such that FD cross I is equal to E cross I, and FD dash cross I is equal to E dash cross I. Okay. This was shown by using a normal form of a surface link. The following is the application of this theorem, triviality theorem. Surface link, this is just in some sense a corollary. Surface link F is trivial if the fundamental group of F is a meridian-based free group. Next, the stable force field of genus N is a four manifold. Sigma or sigma n, which is the connect sum of S4 and n copies of S2 cross S2. An orthosphere pair on the stable four sphere sigma is a pair of two spheres S and S dash embedded in S4, which meet transversely at just one point with intersection number one, uh, and with the self-intersection number of S and S dash zero. Okay. Uh, Pseudo-orthosphere basis of the stable four-sphere sigma of genus N is the system S star S dash star of N disjoint orthosphere pairs SY dash in sigma. The region of a pseudo-orthosphere basis S star S dash star in sigma of genus N is a unique simply connected four submanifold omega in sigma obtained from N disjoint regular neighborhood of the union SY and S dash I in sigma by connecting along disjoint 100 in sigma. Omega C be the complementary region of omega in sigma, which is a homotopy 4 ball. Pseudo-orthosphere basis is an orthosphere basis of sigma if omega C is diffeomorphic to the 4 ball. Consider sigma n as the double branched covering space of S4 branched along a trivial surface knot F of genus N in S4. Then the lift of every O2 handle core basis D star D dash star on F in S4 is an O2 sphere basis of sigma n by the uniqueness of an O2 handle pair, from which the following result is obtained through deformation arguments of two spheres in sigma n. The orthosphere basis theorem, which says every pseudo orthosphere basis S star S dash star of sigma is an orthosphere basis of sigma. For every smooth homotopy four sphere M, there is an orientation preserving diffeomorphism from kappa from M connect sum of M and sigma n to sigma n for some n by Wall's theorem, which defines a smooth embedding J from compact once punctured manifold sigma n0 of sigma to sigma n. By orthosphere basis theorem and self theory, J extend to a diffeomorphism J plus from sigma n to sigma n, meaning that M is diffeomorphic to S4. So for the sphere theorem, every smooth homotopy for sphere M is diffeomorphic to the fourth sphere S4. Next, the following free ribbon lemma is useful for our application. Every S2 link K with fundamental group, free group, is a ribbon S2 link. Now, there are four different proofs of this lemma. Disk bound system in the four disk D4 is the union of trivial proper disk system D in D4 and disjoint bound system B in the boundary 3 sphere, spanning the boundary trivial loop system, boundary D, okay, which is an improper disk system. Ribbon disk link is a proper disk system LD in D4 obtained by an interior push of the improper disk system into the interior of D4. There are two observations. Observation one is every ribbon S2 link K in S4 is the double of a ribbon disk link KD in D4. Then the inclusion of the ribbon disk link KD to the ribbon S2 link K induces an isomorphism of the fundamental groups. Observation two is if the fundamental group of the ribbon S2 link K is a free group of rank n, then the four-manifold Y obtained from S4 by surgery along K is diffeomorphic to sigma n, okay, which implies the second homotopy of the disk link KD is vanishes. Essentially, this means the following ribbon disk aspherical theorem, which says let KD be a ribbon disk link in D4, then the exterior of KD is aspherical. In particular, the fundamental group of ribbon disk link KD is Tojo-free. So the corollary is obtained. The fundamental group of every ribbon S2 link is Tojo-free. One full subcomplex of a cell complex P is a subcomplex PF of P, such that the one skeleton of PF is equal to the one skeleton of P. So the following for the realization theorem is obtained. For every contractible finite two-complex P, there is a ribbon disk link LD in D4 with free fundamental group, such that the one skeleton P1 of P is a spine of the exterior of LD, and when exterior of LD is regarded as P1, the one skeleton of P by 1, every one full two subcomplex PF of P is a spine of the exterior of a sublink LDF of L. In particular, P is a spine of DF, D4. So the corollary of this for the realization theorem, every connected subcomplex of every contractile finite two complex is aspherical. Apply a similar argument to the universal covering space of an aspherical two complex, then asphericity theorem is obtained, which says every connected subcomplex of every aspherical two complex is aspherical. Next, weighted system of a group G is a system of element Wi whose normal closure is equal to G. The weight of G is the least cardinal number of a weighted system of G written by Wg. Let G star Z be the free product of G and the infinite cyclic group Z. Let F be a compact connected orientable proper no separating surface F, the surface in not exterior E, and E plus be the quotient 3 complex of E by identifying a normal line bundle of F cross I with a point. The following two theorems are known. First one is Gonzalez Acuna and Ramirez. The weight of G and G star Z is greater than 1 for every non-trivial group G, if and only if conjecture Z is true. Conjecture Z says the fundamental group of E plus is isomorphic to Z for every not exterior E and every compact connected orientable proper non-separating surface F in F. Next theorem is a Kawauchi theorem, which says if G is Tojo-free and the weight of G star Z is 1, then G is a trivial group. It is shown that weight of the fundamental group of E plus is 1, and there is a connected to subcomplex C dash over a finite contractible to complex C, such that the fundamental group of E plus is the free product of the fundamental group of C dash and Z. By corollary to 4D realization theorem, the fundamental group of C dash is Tojo-free, so that by classical theorem, the fundamental group of C dash is trivial. Hence, conjecture Z is true. Thus, group weight theorem is obtained, which says weight of G star Z is greater than 1 for every non-trivial group G. Next, the span for the manifold X over homotopy 3-sphere M is given by the union M0 cross S1 and boundary M0 cross D2 for a compact once-punctured manifold M0 of M, which is diffeomorphic to the 4-sphere by 4D sphere theorem. By a Hegardt splitting of M and free ribbon lemma, the following span ribbon lemma is obtained. The span, which says the span torus knot Tk equal to K cross S1 over knot K in M0 is a ribbon torus knot in the 4-sphere X. This implies a 3D engulfing lemma. Any knot K in a homotopy 3-sphere M is contained in a 3-ball B of M. The following famous Bing theorem, which says if a homotopy 3-sphere M has a property that any knot K in M is contained in a 3-ball B of M, then M is diffeomorphic to the 3-sphere. Thus, the following 3D sphere theorem is obtained. Every homotopy 3-sphere M is diffeomorphic to S3. Next, for a link K in S3, a slice surface for K is a compact oriented smooth proper surface without a closed component in D4, bounded by K. A slice surface E for K is a ribbon surface for K if there is a bound surgery sequence from K to a trivial link in S3, whose upper closed realizing surface E dash in D4 is equivalent to E. Okay? Note that there are lots of non-ribbon surfaces for any given link K. The following normal form theorem is well known. Any slice surface E of any link K is equivalent to a slice surface obtained from a ribbon surface E dash for the split sum K and a trivial link O in S3. By adding a disk system D bounded by O in S3 and then pushing D into the interior of D4. The double F of E dash is a ribbon surface link in S4 whose middle cross section is the split sum of K and O, which admits an O2 handle pair system D cross I, D dash cross I with interior intersections, where D cross I is a cycling of a band system connecting to O, and D dash cross I is a cycling of D. There is a method to remove the interior intersection of D cross I, D dash cross I by sacrificing an equivalence to F. Thus, there is a ribbon surface link F dash in S4, which is a linear embedding of F, such that the middle cross section is K plus O. K and is a split sum of K and O. And the O2 handle pair system, K cross I and D dash cross I, has no interior intersection. This means a classical ribbon theorem, which says given any slice surface E for any link K, then there is a ribbon surface E dash for K, which is a linear embedding of E. Next is a final section. A stabilization of a surface link F in a connected sum of F and a system of trivial torus knots. A stable ribbon surface link is a surface link F such that a stabilization of F is a ribbon surface link. Every surface link is equivalent to a stabilization of a surface link F star with minimal total genus. This surface link F star is called a handle irreducible summand of F. The stable ribbon theorem is obtained. Any handle irreducible summand F star of every stable ribbon surface link F is a ribbon surface link, which is determined uniquely from F up to equivalences and stabilization. In abstract, I state that any S2 link of trivial component is a ribbon S2 link without restriction, but this was felt, in fact, by Ogasa's observation. There was a non-ribbon S2 link of trivial component. Thank Rental for pointing out this. For a surface link F with R component, a fusion surface knot of F is a surface knot obtained from F by surgery along R-1 disjoint 100. The revised result is the following theorem. Let F be a surface link consisting of ribbon knot components. Then F is ribbon if and only every fusion surface knot of F is ribbon if and only any one fusion surface knot of F is ribbon. So finally, I have mentioned a lot of results on ribbon surface links, but if I'm missing something or you find a counterexample, please let me know. Thank you very much for your attention. A little early, but I finished. Okay.